Hi everyone, I'm Isabel Fendley, a postdoc at the University of Oxford, and I'm excited to share some of my work with you all today, which has been creating and exploring a global compilation of volcanic sulfur isotope measurements from across tectonic environments. We started this project a couple of years ago as part of the CITER program, and it's really grown since then, and it's been great to work with researchers at a range of career stages from across the world. So as you all know, volcanic volatile emissions are one of the ways that volcanoes impact the environment, and volatiles are also an important part of volcanic eruptive processes. Sulfur is one of the most abundant volatiles, and volcanoes are a critical part of the global sulfur cycle, as they transfer sulfur from the mantle and subducting crust into the atmosphere and surface environment. So understanding volcanic sulfur is really relevant for many different facets of volcanology. Luckily for us, sulfur has several stable isotopes, the most abundant of which are 32 and 34 sulfur. Sulfur isotope composition of volcanic materials is affected by two primary factors: the original source of the sulfur and its isotope composition, and then the volcanic processes which sulfur undergoes, particularly degassing and precipitation of solid sulfur phases. So as a little refresher, when we talk about sulfur isotope composition, we use delta notation, which is based on the ratio of the unusual isotope, in this case 34S, relative to the common isotope, 32S. So delta 34S is always with respect to a standard, which for sulfur, the reporting standard is VCDT, or Vienna Cannon Diablo Troilite, which is an iron sulfide from a meteorite. And delta is always in parts per thousand, or per mil. I'll also always indicate the species analyzed, which is usually total sulfur, but also sometimes sulfur from sulfur dioxide or from H2S. So the first control on volcanic sulfur isotope composition is the composition of the original source of the sulfur. And so volcanic sulfur can originate in the mantle, which has an isotope value of around -1 per mil, but it can also have sulfur from ocean sediments from a subducting slab or assimilated in the crust. And sedimentary sulfur can have a wide range of values. Mostly these very positive values from sulfate originally derived from seawater, which is between around 15 to 22 per mil. But it can also have very negative values coming from sedimentary sulfides. And in addition to the original source of the sulfur, volcanic sulfur isotope composition is also affected by volcanic processes, in particular degassing and precipitation of sulfur for minerals. And these processes get pretty complicated pretty quickly, but the important takeaway is that sulfur isotope composition of both gas and the melt evolve during degassing, and so they can provide key insight to the extent of degassing and also to the redox state. In addition, the sulfur isotope composition of the gas is also sensitive to which gas species it is. So sulfur dioxide will be isotopically heavier than hydrogen sulfide and have a higher delta value. And then the difference between these two is temperature dependent, and we'll touch more on that later. To investigate and compare volcanic sulfur from different volcanic systems around the world, we set about compiling all the measurements we could get our hands on. And in this analysis, we've included around 1,500 total measurements from around 100 volcanoes around the world, including measurements of both gas of different species, as well as rock data from both bulk rock and melt inclusion analyses. So let's explore the large-scale trends in the dataset by looking at all the data together. So the first pattern that jumps out at you is that these red data points, the data from ARC systems, tends to be more positive in sulfur isotope space than data from hotspots or other tectonic environments. It also seems to exhibit a larger range of values, even for a single volcano. And that more positive pattern is particularly apparent when we now look at just the median of total sulfur isotope composition for each volcano, now grouped by global region. In addition, that increased variability seems to also matter at the regional scale, where we see a larger range of values reported between volcanoes in each region, which is comparable to the entire variability from hotspots around the world, shown in those blue dots. So to further investigate the cause of those positive values, we further investigate the source by adding barium to lanthanum ratios to our compilation whenever possible. And so barium over lanthanum reflects input from the subducting slab, with higher values indicating more slab contributions. So hotspots and more predictably plot low in this space. And we can also see here that many arc systems follow a positive trend, with increasing delta values also reflecting increase in barium over lanthanum. And this together represents sulfur that's most likely coming from slab input. However, not all of the arc systems follow this trend, and that there's this group here which plot sort of low to medium barium to lanthanum values, but are still high in sulfur isotope space. And what causes this is still an open question, but it's potentially reflecting sulfur that's assimilated from the crust more locally rather than being from the subducting slab, or that the sulfur isotope composition has been affected by degassing or hydrothermal processes. The second pattern that we note that's a little bit more hard to see in the larger plot is that hydrogen sulfide values are consistently lower than those from sulfur dioxides. And so you can see that in the density plot in the lower right, which is all of the values grouped together regardless of volcano. Now we can see this same trend when we examine only the gas data and we plot it along with the temperature of collection. In general, as temperature decreases, the isotopic difference between the two species is increasing, consistent with increasing fractionation at lower temperatures as we would expect. Now we can represent the difference or amount of fractionation with a fractionation factor, alpha, when we have paired analyses, so both species at the same place at the same time. And we can calculate these alpha values for each of those data points and compare it with this theoretical fractionation curve in the lower plot based on laboratory experiments. And what we see is that a lot of the data points, a lot of these calculated fractionation factors are actually plotting off the line. They're not in equilibrium with their collected temperature. And most data is above the line, so is likely less in equilibrium at a higher temperature than at what it's currently being observed at. In conclusion, we've presented a global compilation of volcanic sulfur isotope values from across tectonic environments, and we've demonstrated that, as expected, sulfur from arc systems is isotopically heavier in general than sulfur from hotspots, but it has a lot more variability. And also that sulfur in gases, in many cases, is not in isotopic equilibrium with the temperature at which it's collected. And stay tuned, we have other parameters in this dataset which we are currently analyzing.